Hello friends, we have to start next topic, hydrostatic paradox. Hydrostatic paradox means the pressure exerted by a liquid depends only on the height of the liquid column and does not depend on the shape of the containing vessel. Pressure exerted by a liquid depends only on height of that liquid column, how much height of that liquid column, and it does not depends on shapes of that liquid columns, means how much shape we have to use of that containing vessels. Therefore in hydrostatic paradox, the pressure exerted by a liquid depends only on the height of that liquid columns, does not depends on the shape of containing vessel, and that is called as hydrostatic paradox. Next concept, Pascal's law and its applications. First we have to see Pascal's law. The pressure applied to any point of an enclosed fluid at rest is transmitted equally to every point of the fluid and also on the walls of the container, provided the effect of gravity is neglected. For example, suppose if we have to take the toothpaste and we have to apply the pressure on any point of an enclosed paste or enclosed tube, then that fluid or paste is transmitted equally to every point and also the walls of that tube, and this is the Pascal's law. This is the example of Pascal's law. Applications of Pascal's law. First application, hydraulic lift. It is used to lift heavy objects using a small force. Hydraulic lift, and this lift is used to lift heavy objects using a small force. If we have to apply this small force, then also heavy objects we have to use by we have to lift by using this hydraulic lift. It works on the Pascal's law. This hydraulic lift, it works on the Pascal's law, means we have to apply the small force, then overall force is transmitted. It consists of a tank containing a fluid fitted with two pistons, S1 and S2. S1 has a smaller area of a cross section A1, while S2 has a very large of cross section A2. That is, A2 is greater than A1. A2 is greater than A1. A small force F1 is applied on the piston A1. Small force F1 is applied on the piston A1 is in the downward direction. It will exert pressure P. This pressure will transmitted to the piston S2. Therefore, from figure we have to write here P is equal to F1 upon A1 and P is equal to F2 upon A2. Then by using Pascal's law, again here same concept, we have to apply the force, then that fluid is transmitted to the equally to every point of that fluid. Therefore here by using Pascal's law, F2 upon A2 is equal to F1 upon A1, and then rearranging these terms, F2 is equal to F1 inside bracket A2 upon A1. As A2 is greater than A1, hence F2 is very greater than F1. Thus, heavy load placed on S2, heavy load is placed on S2 can be lifted up or down by applying a small force on S1. Next, application of Pascal's law, hydraulic brakes. Now here hydraulic brakes are used to slow down or stop vehicles in motion. It used to hydraulic brakes are used to slow down or stop vehicles in motion when small force F1 is applied on the piston of a master cylinder. The pressure P1 is exerted. This pressure is transmitted equally to solid cylinders P2. As the area of cross section of solid cylinder is much larger than the master cylinder, therefore greater force is applied. It causes compression of friction pad of wheel, due to which speed of wheel decreases. Compression of friction pad of wheel causes, therefore speed of wheel decreases. Therefore P2 is equal to P1. Therefore P2 is equal to F2 upon A2 and P1 is equal to F1 upon A1. Therefore we have to rearranging F2 is equal to F1 inside bracket A2 upon A1. As A2 is very greater than A1, hence F2 is very greater than F1. Next topic, measurement of pressure. Instruments used to measure pressure are called as pressure meters. Is also called as pressure gauge or vacuum gauge. For measuring pressure, we have to use the pressure meters or pressure gauge or vacuum gauge. First one is mercury barometer. A barometer is a device used to measure fluids in motion. Atmospheric pressure. A long glass tube about L meter long. A long glass tube about L meter long is filled with mercury. It is inverted into a bowl of mercury. The mercury column in the tube stands at a height h, for which the pressure at point A inside the tube due to weight of mercury column is equal to the atmospheric pressure P0 at point B. The space at the closed end of the tube is nearly vacuum, so the pressure there can be taken as 0. The space at the closed end of the tube, is nearly vacuum, so the pressure there can be taken as a 0, and that is, this space is called as Torricelli's vacuum. Therefore PB is equal to PA. PB is equal to PA. Therefore P0 is equal to PO is equal to H rho G, where H is the height of mercury column, rho is the density of liquid column, and G is the acceleration due to gravity. It is found that mercury column in the barometer has a height about 76 cm of Hg or 760 millimeter of Hg. Second, open tube manometer. A manometer consists of U tube partially filled with low density liquid, and that is the water or kerosene. One arm of a manometer is open at the one arm of manometer is open to atmosphere and other is connected to the container D whose pressure to be measured. Therefore, from figure PB is equal to PC, means pressure at point B is equal to pressure at point C, both points at the same level. Therefore, PA is equal to P0 atmospheric pressure. Therefore, we have to write PB is equal to PA plus H rho G. Here PA is equal to P0. Therefore, we have to write here PB is equal to P0 plus H rho G. Again here PB is equal to PC. Therefore, put here PB is equal to PC. PC is equal to P0 H rho G. The pressure in the container is P is equal to PC. Therefore, put here PC is equal to P. Equation becomes P is equal to P0 plus H rho G. As the manometer measures gas pressure of the gas in the container, hence pressure in the container is P minus P0 H rho G. Rearranging this equation, then we have to get P minus P0 is equal to H rho G. Thank you.